is E. Okay? That's the definition of the order of an element as distinct from the order of a group. Okay. So you have to prove that this subset is in fact a subgroup of this group G. So how do you do that? Okay, so how to do that? So let M and N be any two members of your group, okay, and we have to show that Mn, the product of them, is also belongs to the group, or belongs to H. Sorry, this should be an H. Now it's wet. So okay, so take any two members of your subset H, they're of this form, and you have to show that the product of those two, when squared, is E. So what you're trying to show that the product also belongs to H. Okay? So show that this Mn belongs to H. I can't write it because it's not dry. Okay, so Mn belongs to H. And how do you do that? How do you show that Mn belongs to H? By showing that the square of it here, the square of it is E. So I have to show that Mn squared is equal to E. You follow that logic? Right. So show. Maybe my pen is dry. Let's see if this one works. Okay. So show that Mn squared equals E. We have to prove that, and if we can do that, then we've shown closure. Okay. All right. So Mn squared is just Mn. Okay. Now M and N belong to H. Okay. And if M and N belong to H, they belong to G. Okay. Because this is a subset of G. Right. Now, if M and N belong to H, therefore M and N belong to G, but G is abelian, right? So we have this. So Mn also do this. So Mn equals Nm. So let's switch these two around. So instead of Nm, we can say it's Mn. N. But that then is just M squared, N squared. Okay. Now M belongs to H, so that means the square of M is E. So that's E, right? And N also belongs to H, so that means, because of this, so that means N squared is E, and the answer is just E. Okay? So we've proved that Mn squared is equal to E. And therefore, Mn belongs to H, right? Because it has the square of it. The square of it is E. So Mn also belongs to H. Therefore, it's closed. Okay. The unit. What's the unit? Well, E. It's just E, right? It's the same unit as G. Why is that? Well, E squared is E, right? D by E is E. So if A is E, the square of it is E. So that means, so that implies E belongs to H. Okay? So this H has a unit. So it's closed, it has a unit. We don't have to prove associativity because G is associative because it's a group, right? So we only have to test these three things. We don't have to worry about associativity. Now, what about the inverse? How to prove? So the inverse. So if M belongs to H, how to prove that the inverse also belongs to H? So how to prove that? Now, if M inverse belongs to H, if M inverse belongs to H, that means that M inverse squared equals E, right? Because that's the condition. If this element here, if it belongs to H, it means when you square this, when you square it, you get E. So M inverse should be E. Well, let's try and prove that. Okay. So M inverse squared. That's M to the minus 2, right? They're just the exponents. Now M to the minus 2, that's the same as M squared. Hold on. Is that right? You just multiply them, right? Yes, okay. Now, so M squared to the minus 1. Now, M squared, we know, is just E. And the inverse of E is just E. So we've done it. Okay, so for each M, there's an inverse. Right? So that means the inverse belongs to H. Okay? So therefore, M inverse belongs to H for each M. Okay? So we have all the inverses, and therefore, this set here, the set of the elements belonging to G that have order 2, right? That's what that means. The order of this element is 2, and you have the set of, you have your group G with all its elements, and you pick out those elements that have order 2. So, like, say this one, call it A, and its order is 2. Therefore, A squared is E. So you collect all those elements that have order 2 that have this property. Remember, there's two ways to specify a set. One is you just write out the list, and the other one is you specify a property or properties that the elements have. Well, here's the property way of specifying the set. Okay, all right. So that's done. Proven. Okay, true or false? The author seems to like true and false type questions. Okay, is this true or false? A non-abelian group can have a proper abelian subgroup. Ooh. So a non-abelian group can have a proper abelian subgroup. So all you need to do is just find one example where that's true, and then that statement is true. Now you have to think about it, but to save time, here's a group, right? Here's a group table, and a non-abelian group. Now is this abelian or non-abelian? Well, let's try something. Let's try like X Sx. So we do S first and then X, and we get Y. Right? So Sx gives you Y. So you do S first and then X. So S, X, yeah, you do X second. S first, X second gives you Y. Okay? Now do it the other way. Now do so S. No, X, S. So X, S, X, S.